Yes, I think we can start now. Good afternoon, everyone. Welcome to the fourth MULTHEM training session on life cycle assessment for multi-material products. Our first talk will be presented by Gustavo, and the second talk will be given by Joman. Before we get started, I would like to go through some general housekeeping. I would like to encourage all of you to keep your mic on mute during the presentations and reserve your questions until the end of the full training session. At the end, you can unmute your mic and direct your questions to the trainings, or alternatively, you can use the chat box to type in your questions. I would like to start the training session now and pass it to our first presenter, Gustavo.
Hello, and thank you very much for the introduction. So I'm going to share my screen now, if it's okay for you. Window. Please let me know if you can see it. Can you see my screen?
Yes, I can see it. Yes, I can see your screen.
Okay, I'm spoiling everything. Sorry for that. Are we good?
Yes, all good.
Okay. So welcome everybody, and thank you very much for joining. My name is Gustavo Larrea Gallegos, and I am a researcher at the Luxembourg Institute of Science and Technology. My main area of research is life cycle assessment, and that's the reason why this first part of the workshop will be focused on what is life cycle assessment. So a first quick disclaimer, this is not a course on LCA or life cycle assessment. It's just designed to give you a brief introduction of what are the basic concepts and the things that we should know when we talk about LCA, so we can prepare you a bit for the results that are going to come later, and also for the results in the context of the MULTHEM project. So even if you have questions about the presentation, I think we can keep it for the end of the two presentations. So my talk is going to be divided in 3 steps. Mainly at the beginning, I'll just provide a brief presentation of the history of life cycle assessment and how we went from the end-of-pipe approach to the life cycle thinking approach, which is what rules life cycle assessment. Then we'll discuss a bit what is LCA as its standard definition, and then we will talk about a bit about what are the stages of life cycle assessment. So the approaches that we had when dealing with different environmental projects during time have changed. For example, in the year 70s, most of the pollution problems, such as acid rains, eutrophication, and health diseases, were addressed by developing technologies for waste treatment, site remediation, and recycling. These approaches are called end-of-pipe because most of the solutions were aimed to decrease the amount of the contaminants at the production at the end of pipe before they were released to the environment. As we can see on the right-hand side figure, if we think about how actually something is being produced, everything comes from nature. The resources come from nature, then they go through a probably very complex supply chain, including logistics and production of ingredients. And then they pass to the factory where a product is being produced, and then the emissions or the effluents are released to the environment. So in this approach, the main target was to decrease these contaminants at the end of pipe. Now, this was very useful, but the main problem is that it lacked a holistic view, meaning that most of these solutions were very site and sector specific. And in some cases, they were simply moving the pollution from one environmental compartment to another environmental compartment. For instance, if we had a factory that wanted to decrease the emission of certain substances, they would rely on filters. But at some point, they will need to change the filters, so they creating more residue that needed to be treated in a landfill. So in other words, we were moving the pollution from the air to the soil. So another aspect of these approaches is that they were mainly mass-oriented. So the orientation was on the amount that was released, on the concentration in some cases, not so much on the effects that it produced. Also, they were not comprehensive, meaning that many environmental problems were neglected through this very narrow, limited vision. So a year later, in the 80s, this concept of environmental management appeared. that appeared as different schemes as part of the standard ISO. And this was an improvement, yes, because now the approach was not only on the end of pipe, but also it had a site approach, so it's bigger. It involved the accounting and management of energy and raw materials demand, and also the pollutants at a factory level, not only end of pipe. It, of course, encouraged companies and agents to implement procedures and actions and commitment to improve continuously. This is again useful, but it lacked a holistic view because, again, it was limited to consider only the supply chain or the factory that produced the product and the end of life treatment. But it's not considering the other suppliers and the other aspects that are outside of the production bubble. At the same time, it was focused on few pollutants and few effects were considered. This is the reason why in the 90s, the concept of life cycle thinking appears. Well, more than appears, it gets formalized as a family of standards, part of the environmental management family. So the idea of life cycle thinking is basically go from the end of pipe to a more product approach. So the logic here is to have a assessment of all the environmental impacts that are related with the life cycle of a product. Well, not only products, could be services, processes, yeah. And when we say life cycle, as we can see in the right-hand side figure, we are not only talking about the end of pipe, like the emission or the emission of the contaminant, but or the factory or the supply chain, but we consider everything from cradle to grave, from the beginning, from the resource or natural resource to the end of life of the product we are studying. Since then, this approach was basically guiding the implementation of tools in the context of sustainable development, and also the design or the redesign of more environmentally sustainable products. Of course, the life cycle assessment is born from this. Life cycle assessment is a methodology that implements the life cycle thinking in its core. So the idea of life cycle assessment is that now it can help us to avoid this transferring of pollution, because we are not focusing on just one stage of the whole life cycle, but we consider the whole life cycle as in our boundary of analysis. At the same time, the logic of life cycle assessment is that it can allow us to conduct fair comparison among alternatives. I will explain in some slides later that the way how the method is set and the guidelines that are provided helps us to have real fair comparison. And when we can do fair comparison, we can do design, we can redesign products, we can propose new alternatives. Finally, it provides it's a bit more comprehensive for sure, because now the scope on life cycle assessment is to have a multi-criteria vision rather than just a mono criterion. For instance, in LCA, we can not only address carbon footprint or water footprint, we can assess at the same time different impact categories and make decisions based on those results. So this is the history of LCA. And in practice, the first documented implementation of LCA was done by a company. It was Coca-Cola in 1969. And this is a very, very famous example in which the company wanted to design or redesign their packaging. And they were trying to understand which type of packaging was better and who should be the one making the packaging. So for that, they used life cycle assessment. Of course, back then, it was not defined as life cycle assessment, but it implemented these principles of life cycle thinking. In the study that they presented, they used two indicators that are also used now, but maybe not the mainstream: community energy demand and also materials demand. Now LCA is more mature for sure, and there are many more indicators or metrics or impacts. I'm just using proxies now. For those who are interested on learning more about the history of LCA, I put some nice papers there. So what is LCA now? Life cycle assessment is a standardized methodology that can be summarized as as a compilation and evaluation of the mass and energy inputs, outputs, and the environmental impacts of a system throughout its life cycle. I think that the previous example that I presented before is quite clear. In life cycle assessment, we want to consider the whole lifetime of a product from the natural resource to the natural resource in its end of life. It's quite mature now. There are different standards that rule the methodology. All of them belong to the ISO 14000 environmental management family. And for those who are looking for information, I'm sharing the standards that are now being used in LCA. And of course, that I use now to make this presentation as well. Now, the common usage that we have now for LCA is mainly to give support to companies and policymakers. And this can be done, for instance, when companies want to design or redesign products. For instance, I took this example from the manuscript that I'm sharing here, in which the company and researchers wanted to redesign or to substitute a container of a product, which is this tube, this container. And for that, they use life cycle assessment to determine all the inputs and outputs throughout the whole supply chain, throughout the whole life cycle of the product. With that, the researchers found two, let's say, environmentally optimal alternatives in which they basically evaluated different strategies. For instance, for the alternative 2, the tube 2, they decided to replace the virgin plastics by mineral fillers and recycled plastics. For the tube 3, they decided to reduce the thickness of the material. So the logic here is that with LCA, we can observe, we can have different parameters to redesign our product, and that's actually how a lot of companies are using it now. So this is just an example. You can find many similar use cases in the literature. Now, some companies use it to redesign their products, but they can also use it to redesign the supply chain and the whole production system. That's the case of Fairphone. This company produces sustainable phones, if I can call it. They have a different, a particular business model, and they do life cycle assessment not only to design the phone itself, but also to design the whole supply system. So thanks to the results of LCA, they can determine which suppliers are better, or which alternatives or which technology they should use when sourcing their goods. Now, since we can quantify the impacts into numbers, life cycle assessment has also been used to inform the consumer, to give information of the impact of a product that a consumer is buying. This is done with this period of transferring some responsibility to the consumer. So when selecting a product, the promise is that a better informed consumer can take better decisions. And this is done through something called eco-labels, which are standards that set how different impacts should be accounted and reported. So then producers can put that information in the products, and the consumer can then easily compare the supermarket. Yeah. Finally, LCA is used as well to guide policy making and basically identifying better technologies and strategies for the future. And here in this example, I brought a screenshot of a very nice article in which the researchers use life cycle assessment to study the whole production of biochemicals. Yeah. And here, what they found, and it's kind of a counterintuitive conclusion, is that not all biomass is necessarily carbon neutral. So in this case, life cycle assessment was fundamental to understand the real environmental impact of a particular system or product in this case. And the literature is also not abundant, but it can show evidence of some counterexamples in which some evident green solutions are not really that green. And life cycle assessment can help us to clarify these doubts. Okay. Now, as I mentioned before, we have the ISO. The ISO gives us an overall framework of what LCA should be about. It also gives us a list of minimum quality requirement that we must report to comply with this standard. However, ISO doesn't tell us what methods to use, what formulas to use, what equations to use. But it it gives us a methodology, like the diagram I show here, and which defines how LCA, standardized LCA, is done. So there are 4 stages in any standardized study. The first one is the goal and scope definition, which basically consists on defining what is the objective of the study, what do we want to study, for what we're going to do the assessment. The next stage is the life cycle inventory stage, which consists on modeling, which is the backbone, I guess, of the LCA study, modeling the whole system, the supply chain, gathering data. Here we have to gather production data, supply chain data, chemical data, emissions data, environmental data, etc. The third stage, the life cycle impact assessment, basically consists on translating all those flows that we gathered in the previous stage into impacts that mean something for us. So these 3 stages, as you can see with the arrows, are sequential, but are meant to be iterative. So the last stage, results and interpretation, is connected to all of them, because life cycle assessment is meant to be I repeat, iterative methodology. So we are constantly modifying the LCI, constantly modifying the LCIA, sometimes redefining the goal and the scope, because designing an LCA model requires that iteration. So as I mentioned before, some direct applications are product development, policymaking, marketing, and strategic planning. And these applications, of course, are part of the result and interpretation step. So in this talk, to make it brief, I will go briefly through the different 3 stages, and I'll try to explain super fast what are these stages about. The first stage, goal and scope definition, basically states what is the intended application of the LCA results. It has to be precise and ambiguous. This stage is very important because the quality of the LCA study must be coupled with the goal of the work. Now, for example, if we want to compare the impacts of 2 different detergents, we expect to have some LCA result that helps us to with this eco-design purpose. So if our objective is to evaluate these 2 for eco-design, the LCA result should give us that information, should be planned in that direction. This seems like a quite straightforward example, but we can also have some more complex examples. Like, for instance, we can also use LCA to evaluate the impacts from the introduction of electric vehicles into the mobility market, and we want to give this result to support the national policy. So if we want to do this, the result of the LCA should depict at least a comparative LCA of electric vehicles and other mobility alternatives, such as combustion engine vehicles, etc. So as what I'm trying to mention here is that when we define the goal of the LCA, we need to also couple it with the expected results. Since it's an iterative methodology, when we start doing an assessment, of course, we modify the goals so it can fit the results, or vice versa. One important step in this process is the definition of the function of a product. The function of a product is related to the needs of the final user of a product, such as if we are doing an assessment of a telephone or a car or whatever it is, we need to consider the comfort, duration, or the criteria that is required by the final client, the final user. It has to do with the objective of the study, obviously, and it helps us to determine what is the scope of the study, like how much we want to cover with this study. This is very important because once we define the functional unit, we can start comparing different products that fulfill the same functions. And of course, it needs to be quantifiable. In LCA, this functional unit quantifies the service that is delivered by the product system. Products that do not fulfill the same functions are not comparable. And this is very, very important when we do an LCA. Also, any comparison must be done on an equivalent function. For instance, if we take the example of the detergent again, we can ask these questions to set our function of the product, like what or which product? Liquid detergent. Name XX of the brand YY. How much and how long, in which conditions of use? we can set and say 1 cleaning under average operation. How well, for which function, is going to be cleaning car body in a car wash system. So by doing this, we can set the functional unit as cleaning one time, 1 average car body in car wash system under average operation using the product XX produced by YY. This is very important because now if I want to compare the product XX with another detergent, let's say ZZ, this can only be done considering the functional unit. That means that I cannot compare 1 liter of XX and 1 liter of ZZZ. We need to compare 1 cleaning with XX and 1 cleaning with ZZ. This is very important. In some cases, the example for this example, maybe it's easy to understand. In some cases, it's a bit difficult to determine the right functional unit, especially we have some products that are multifunctional. So the idea here is to understand the steps that we need to follow for this. The second step is the life cycle inventory step, which basically consists on building and modeling the supply chain model that I mentioned, and accounting the amount of consumed natural resources and emitted pollutants during the whole life cycle related to the function that I explained before. In practice, it looks something like this. I mean, every LCA starts with pen and paper. You draw on a paper your system, in which we basically separate the system into 2 spheres, something called the technosphere, this virtual space that contains all anthropic entities, and the biosphere or ecosphere, all the ecological or net natural entities like biome and natural resources. So as you can see here, the red lines indicate flows that go from the technosphere to the ecosphere, which are commonly pollutants or also extracted resources, and the black lines indicate exchanges through the technosphere, which are finalized products. Now, in many situations, our product itself could be in the middle of a bigger value chain, but could also be at the end of the value chain. In life cycle assessment, we should evaluate everything, but then we can also choose to define some limited boundaries for our study, as long as it satisfies the purpose and the goal of our LCA. In practice, of course, we have to model the whole production system, which means that we need to consider the flows in the technosphere among factories, companies, and different other anthropic entities. Also, the extraction of resources, the emissions to the air, to soil, and to water. But in practice, we cannot model the whole world. It's very complicated. So most of the LCA effort is commonly done on modeling the foreground. The foreground consists on this subset of the whole supply chain that on which we have control, that we can gather data, that we can model, and that's basically our foreground. What about the background then? How do I model the electricity provided by Germany? How do I model steel produced in China? For that, we relied on something called databases. These are LCI databases that already contain their commercial products. Some of them are free, some of them are you have to pay, and they contain information of different processes and activities that we can use to couple into our model. Yeah, so the most popular is called Equinvent. Maybe most of you already heard. That covers the whole world. You have now new Chinese database, Tiangong, Agribalis for agricultural products, Sfera, and the Gabi software for some chemicals and industries, and others. So I'll try to be very brief here. And basically, what we do in a computer is exactly this. We set a product that's, let's say, a bicycle. Then we model the production of the product, which considers the assembly of the product. We also need to consider the production of the components that we need for this bicycle. At the same time, we need to consider the production of those components for this bicycle. Now, of course, this production is not maybe in the same region in which we assemble the bicycle. So that's the challenge when we do an LCI, life cycle assessment. And at the same time, we need to reach the nature and to go to the raw material extraction. So we do not only have to consider the production or transformation processes, but also other services proper to a supply system, like the logistics, transportation processes are also considered and should also be considered into an LCA, into life cycle inventory. Now, this boundary, this system, this approach is called cradle to gate, because here we are modeling from the beginning to the gate, to the product. However, in reality, the product doesn't end there, because the product goes to a user in the use phase, and this user will later, after the end of life of the product, will dispose the bicycle to a landfill. This system, this approach now is a cradle to grave approach. Well, the boundaries of the system are cradle to grave because they consider the production, the origin of the resources, cradle, and the end of life of the resources. So this is a full life cycle. This is very important because then the different products and during the whole life cycle can also be reintroduced into the system. Like if we are modeling a reuse system or recycling of materials, and of course for that we need to consider now it as a circular system. So this is a cradle to grave system. In this diagram, these arrows represent flow of products. These arrows represent intermediate flows that could be flows of products as well, but maybe products that we are not interested in. So we don't consider them in our assessment, but they are part of the model. These lines are the waste flows that are important to determine certain impacts and also to determine how much substitution is going to occur when we produce some components or when we produce our own product. And finally, we need to understand that each one of these nodes or each one of these processes has some emissions to the biosphere. And we need to account for these emissions into the LCA exercise. These are called elementary flows. Now, in practice, we don't use Excel anymore. We use different softwares to build this life cycle inventory because it can get very big. The equipment database has around 21,000 processes. Most of them are connected. So even if you don't want to, you are calling for a reason. Electricity, I don't know, in a very far part of the world because the worldwide supply chain is connected. So there are different softwares. Some of them are commercial, some of them are open source, some of them are even programmatic. You can use in Python and do your LCA in Python. Here I took a snapshot of how it looks to do an LCA in a commercial software. It's called OpenLCA. You define your inputs, also your outputs, and that's how you would do it in normal circumstances. Now, okay, it's a bit late. The last stage is called Lifecycle Impact Assessment, LCA, and basically it's a phase in which we're trying to understand and evaluate the magnitude and significance of this potential the potential environmental impacts of a product system. Now, the idea of an LCA is to quantify the impacts of the lifecycle inventory, meaning that these flows that we diagrammed before, they mean something. All right, so we are trying to quantify it. Also, in this stage, we try to show the consequences that this particular flows and these particular impacts can have in areas of protection that we care about, human health, biodiversity, etc. And also, because of the methodologies and the framework that is defined in this stage, we can make the sources of damage comparable to each other. So the idea of LCA is to convert as I said, the LCI into impacts, but also make these impacts comparable to each other. Now, the LCA framework is defined in the standard, and basically, I'll try to summarize in a nutshell, consists on going from the substance, the emission of the substance, which we get from the LCI, to an area of protection, to a particular damage. This is a quite complex process, of course, like the CO2 emission, the process that CO2 emission takes to then affect human health or affect biodiversity is quite complex. Because of that, we in LCA use two types of metrics or two types of impacts. One of them is called endpoint, which is the final area of protection or damage that we want to understand. And the other one is called midpoint. It's an intermediate point from the emission to the final damage. The midpoint, or going from the emission to the midpoint, it commonly has low uncertainty, is easier to model, and has a higher acceptance. However, to go from the midpoint to the endpoint, it's more complicated because some processes are very complex and it's sometimes very debatable to use endpoint metrics, and the uncertainty can be high. So we do this quantification from emissions to midpoint or endpoint through something called characterization, which basically consists on how much an elementary flow is going to contribute to a given impact. It's a number, it's a factor. Because of that, the potential impact is nothing but the multiplication of the emitted amount of each substance or elementary flow times the characterization factor. We repeat this arithmetic operation along this whole supply chain, and that's how we quantify the impact. Now, there are many methods that or impact categories that we use now in conventional LCA. This is an example of the Recipe 2016 method. As we can see, we have different midpoint impact categories. The most popular, I can guess, it's global warming, but we also have different like human toxicity, water use, ionizing radiation, and others. And the endpoints in this method are damage to human health, damage to ecosystem, and damage to resource availability. And as you can see here, in the middle, we have the damage pathways, which are basically this environmental, sometimes even economic processes that helps us to convert from midpoint to endpoint. There are different methods in the literature, different ways of going from midpoint to endpoint as well. Now, in practice, it's like this. What I explain is something like this. We have the characterization factor for one particular substance. We account for total emissions of that substance. We multiply times the characterization factor, and we sum. And this is done in the computer, of course. But in practice, it looks like this. It's literally an algebraic operation. Finally, we have the results and interpretation stage. Here, I won't take more time, but basically consists on trying to understand the results that we get and to identify hotspots that can help us to modify the goal, modify the scope. Because the problem of doing an LCA is that we don't know which part of the supply chain is more important to us until we do the LCA. So we could be disregarding a particular process in our system, but then if we find out that it's actually very important. So then we need to provide better data, richer data for that particular process. Similarly, we can find that some particular processes are actually irrelevant in our final results. They're either not generating impacts or they're not relevant for the context that we need, so we can provide less resolution to that particular process. So it's an iterative exercise. So this is a super brief introduction. I think somebody talked to me. Yes. And to finalize, it's a very mature methodology, LCA, and now there are different ways of modifying the standardized original version to satisfy the needs of the research question. I brought here a diagram that shows some of the flavors of LCA that we have in the literature right now, and you can have variation of this approach to have a dynamic model, to have a consequential model that it's more like towards causality, predictive models, scenario modeling, etc. So to finalize, there are different flavors of LCA, of course, but all of the flavors that we're going to find in the literature somehow respect this methodology that I presented today. So I'm sorry if I took too much time, and thank you very much for your attention. And now Jomin can continue. Thanks.
Thank you, Gustavo. Very nice. And now I'm going to share my screen.
Yeah.
So you can see the screen, right?
Yes, I can see yours.
Okay. Thank you very much. So now I'm going to bring the LCA to be in terms of what we are doing in MULTHEM. So the content of this presentation will go in this way. So first we will try to define the goal of MULTHEM and also the use cases that we want to study based on the technology we are investigating. Then we have to define the scope of the LCA, like Gustavo already mentioned what this is all about. So now we will be specific for the different products that we are investigating. Then I'll give an example of the LCA results that we have so far for a battery casing that is manufactured conventionally. So that is like the benchmark that then we want to compare to one of our products that we're doing in the project MULTHEM. Then I will have some slides regarding the sustainability advantages of using additive manufacturing, which is one of the technologies that MULTHEM is using. And finally, there is an example of how two different additive manufacturing technologies can be selected based on the LCA. So there's a direct comparison. Like Gustavo already mentioned, this is one type of LCA. So this is what we are doing in the last slides. So the goal of MULTHEM is to use aluminum and composites in additive manufacturing process to produce aluminum composite products that have strength and cooling functionalities. So we have products like this. This is the aim of the project. So we have composites to give strength and lightweight, and we have aluminum to dissipate the heat and also to give strength to the final product. So the aim is to get lightweight and heat dissipation in a single part. So the use cases that we selected in MULTHEM are, the first one is an electric bike battery casing. The second one is a electric motor housing. And then the last one is the radio altimeter housing. So these are all backed up by different companies that are partners of the project MULTHEM. Like Airy Composites is in charge of doing the battery casing redesign. Air Electric is in charge of designing the electric motor housing and also the motors. And Thales is in charge of redesigning the radio altimeter housing. So these companies, they all have a baseline product, and then we are redefining it to apply the MULTHEM technology. In the use case one, we have the e-battery casing. We start with a single material, which in this case is aluminum. Then there is an optimization process. This is being done by different partners of the project, like Brunel University. And then finally, we get with a suggestion of a multi-material lightweight design with composite parts and also sections of aluminum. Similarly, in the electric motor housing, it's something like this. So the first component is a single material, so everything is made out of aluminum in the housing. Then there's the same optimization by doing a thermal and mechanical analysis to see where are the weak points, which needs to be strengthened, which needs to be hotter. And then we propose a redesign of the product having a composite and aluminum case. Finally, the radio altimeter. Here I'm just showing a little section of it because this one's very complicated part and some of the components are highly confidential. So we have an aluminum plate in purple, and then this green square here is an electronic, which is emitting heat. So then there is the same analysis of thermal and mechanical analysis to try to optimize the heat dissipation without restricting the functional strength. And this is one of the examples of how this could be redesigned, the purple one being the aluminum and the green one being the composite material. So now we know the lightweight and heat dissipation are good for the operation of the product, but are they also sustainable? Like if we replace the existing products that are single material by multi-material, will still be sustainable? That's the main question that our package 4 of the MULTHEM project is aiming to achieve and to answer. So all of these products, what we want to know is if multi-material and using additive manufacturing more environmentally friendly, right? So at the end. So for this reason, we are calculating the LCA. First, we will do the single material with conventional manufacturing, and then we will do the comparison to a multi-material with additive manufacturing. So there's different technologies, different materials that are involved in the process. So in terms of the scope and the tools that we are using, so we have the life cycle, And we are going to consider in the scope of the LCA of the MULTHEM project, the raw material extraction, material processing, and the manufacturing. And out of the scope is the distribution, the use, and the recycling or disposal of the products that we are investigating. We're going to use the OpenLCA software, which Gustavo already showed you a screenshot of how that looks like, which is a commercial product. And then some of the data, for example, the raw material extraction, the emissions, and all that stuff that we cannot directly measure ourselves, we are getting from the EcoInvent database. First, let's start with the conventional manufacturing steps. So the first thing we need to identify are what are the steps in order to make your inventory. So the example here I'm providing is the battery casing. So the colleagues have identified that there are different components in this battery casing. There's the component 1 and 2, where all the electronics are connected. Connecting this, there's a sleeve which is called number 3, and that prevents the cells inside the battery to rattling around. And then you have the actual battery case, which is made of aluminum, right? So if we want to compare the manufacturing steps of components 1, 2, and 3, we have the ABS granulate production. So this is made of ABS, polymer. Then this is generally done by injection molding, and then we have components 1, 2, and 3. Then we have, for the component number 4, we have the aluminum production. In this case, we have a specific alloy, which is this is aluminum 6082. And this part is made by profile extrusion, and then there is some post-treatment in order to have like the right tolerances. So there is some milling happening, and then we obtain component number 4. So then we go into the input the material and the output material. So this is part of the inventory in the LCA, and there are different operations, right, that we described in the previous slide. So for components 1, 2, and 3, we have the manufacturing done by injection molding. So the input is ABS material around 410 grams. Then there is, during the injection molding process, there is a loss because then you have certain parts of the injection, the injection gate and all the other components of the feeding of the mechanism that are lost. So there's around 7%, and then we are a final output for all the parts around 380 grams, right? So this goes into the assembly. And in the other hand, we have the manufacturing dough to extrusion. So the input here is the aluminum billet for extrusion, which are around 440 grams. And then we assume here that there are no big losses. So then we have an output of 44 of aluminum extruded profile. Then we take this into the milling process, which we lose around 5%. And then we find the component number 4, which are around 420 grams. Putting everything together gives us a total of 80 grams, right? In the MULTHEM process, what we want to replace is actually some of these from C4 and the C3. So this is what the results for the LCA are looking for the conventional case. So what you can be seeing here, we have 2 indicators, the global warming in kilograms of CO2 equivalent, and the different units. So the more critical are shown here. So the electricity production is shown here with around 5, and then the rest of the operations are 3. But the production of ABS is actually quite intensive in terms of global warming. Similar trend is observed in the acidification, which is another macro indicator, midpoint indicator, like Gustavo mentioned. And the electricity production, again, is one of the main contributors to that. This data is assuming that we are producing this in Germany, and in Germany, there's still a lot of fossil fuels being used in the production of electricity. That's why you get these kind of results. Then in the MULTHEM manufacturing steps, we have the battery casing, which I showed you before. But now we want to combine number 4 plus number 3 into a multi-material structure that looks like this. So the target here will be to lose at least half of the mass. So we'll go from 640 grams to 320 grams. Then the process for the plastic components are the same, except for the ones that are already in component the multi-material. So granule production, injection molding, And then we have new steps, right? So we need the production of aluminum, but we also need the production of a composite material, which in this case is polyamide 6 with carbon fibers. Then we have additive manufacturing, we have milling, bonding, and then we have component 3, 4. So this is what we are doing in MULTHEM. And what we want to discuss is why we chose additive manufacturing, because we still don't have the results for this. This is still on the making. We're still redesigning the part, and this is going to be available at the end of the project. So why choose additive manufacturing? Additive manufacturing is an enabler technology. It can help us reduce the cost, simplify the supply chain, and then also make it more resilient. We can reduce the lead time, and we can increase the sustainability. This presentation, we are focusing on the sustainability aspects, and in this case, we have local manufacturing, so there is no shipping and distribution, on-demand manufacturing, which leads to less storage, less overproduction, toolless manufacturing, so there is no need to manufacture additional molds and other tools to get the final part that you want to produce. So for this reason, it seems that it's a good idea to use additive manufacturing. What are the benefits of using additive manufacturing along the product cycle? So the product cycle is like this. So you have sourcing and processing, manufacturing, distribution, use, and end of life. So if you have in the sourcing, the contribution of additive manufacturing, what you get is the design optimization. So then you use less material, so you need to source less material. Then you have a part consolidation, so then you also simplify your manufacturing chain, and then you have less suppliers, and that will decrease the impact, right? Then in terms of the manufacturing, you have less tools, so less material, less energy that is needed to be used to build these tools like molds. And then on-demand production, which leads to less overproduction and inventory. Then in the distribution, you have on-site production, so there is less travel of the materials, so there is less consumption of energy there. And on-demand production means that you will also reduce the warehousing needed. So then when the time of the use, you have the on-demand production, which is better part availability, and the design optimization, which has better product efficiency. And this is what we are targeting in the MULTHEM project. The end of life will be similar to conventional manufacturing. What are the implications of manufacturing location? So we mentioned about relocating a central point of production to individual sites. And this is an example of a LCA done on the comparison between different production sites. So we have here the production of a standard component in China, which is most of the cases done. And based on the location where this product could be manufactured, then you get different decreases on the CO2 emissions per kilowatt hour, right? If you, for example, produce in Sweden, you have 93%. And why is this? This is because of the energy mix. So depending where you are producing, then you get different sources for producing electricity. So in China, they still using a lot of coal. The USA, they have a lot of gas. So that's why there's a high production of CO2. Germany, there's a greater proportion of the green technologies, but not as good as in Sweden, which has more than half of the energy produced there is done by renewable resources. So the AM could also enable a different supply chain. So instead of having one point of production with a global point of use, as is shown in this schematic, you can have a point of production closer to the point of use. So then there will be less travel and then in the distribution of these parts. So there is also implications on the regional manufacturing. There's a LCA that is being done by this company AM Power and some company in Sweden, where you have the CO2 emissions when you are producing in China, and then you take into account the transportation by air. So you get more than 150 or CO2 emissions per kilogram. But if you were to move your production to Germany and then transport within Europe, then you will have a decrease of 69%, right? So that's quite significantly. In terms of the lead time, then if you produce in China and then you have to ship everything by sea, because then you lower quite a bit your emissions, you're still very high compared to the lead time that if you were to produce your part in Germany and distribute it within Europe. So you have around 70% CO2 reduction by regional production, and the lead time the lead time toward the components is reduced from days instead of months, right? So this is quite important, and it's something that maybe is need to be considered. Then, what kind of AM process which we use, and how the LCA can help us make a appropriate decision for that. So in this case, we're going to compare laser and electron beam energy deposition technologies. This is some work that was on Fraunhofer. And here they have the different supply of the raw materials. So they have the energy supply, the raw materials, the emissions and extractions of material and energy generation. Then the inputs that we're considering to this LCA was the electrical energy, the use of compressor, the material that is used for shaping the part, which is in case the filler wire. And then it was compared to the electrical energy, the compressor, the filler powder, and the shielding gas used for the laser beam powder versus the electron beam direct energy deposition. The test components are the output, and also in this case, there's a bit more waste, so then it has to be considered the powder waste on the laser beam technology. So the energy consumption was measured with a ammonia energy meter. The input emissions data was from the EcoInvent 34 database. The LCA, the software used was the LCA's Open LCA. And then 4 different factors were used for the evaluating the technology. The global warming potential, which is done on carbon dioxide equivalent, eutrophication, which is the phosphate equivalent, then the acidification, which is the sulfur dioxide equivalent, and photochemical ozone creation, which is the ethylene equivalent. This is the type of devices that were connected to the energy supply of the DED electron beam and also from the laser power, so that they have a direct comparison. And what they compare was the manufacturing of a copper cylinder with DED electron beam and DED laser beam. So this is the image of the part that was directly compared between the two technologies. So, and then they measure the processing time, the applied material, and the energy consumption. So in terms of the first indicator, the global warming potential, it was shown that DED goes around 15 CO2 equivalent in kilograms, and the laser was around 45, right? So the main component again is the electrical energy generation. Then there's a contribution of the compressed air and also the filler material that was used. Shield gas was basically negligible, so you cannot even see it in the graph. So regarding the eutrophication potential, you get a similar trend. So DED has the lowest impact compared to the electron beam, versus the laser beam. So acidification is the same, and photochemical ozone creation has similar trends. So as we can see, the EED has a much lower environmental impact compared to the laser base. So there's something that you have to take into account also on top of the limitations of the technology. Just to summarize and give you some indications of our future work that you can expect at the end of MULTHEM. The first thing is that MULTHEM is using AAM to increase the sustainability of multi-material products. So we are redesigning and optimizing for lightweight and also to dissipate heat appropriately. So we are also trying to manufacture locally and on demand. So that's why those are the main reasons why we are using additive manufacturing in MULTHEM. Then the manufacturing step of the use cases have been identified. Now we are in the process of calculating the data. So the first results show that the electricity generation is the highest contributor to CO2 emissions and acidification. And then in the future, we will be comparing the MULTHEM technology with the available technologies that are the current technology, the benchmark technologies. And this will be at the end of the project. The LCA should influence the selection of the process that you should use for additive manufacturing technologies. And as we saw in this example, there's a big difference between using laser and electron beam. So that's just to complicate a bit further the selection of additive manufacturing process, but it's very important if we want to minimize the environmental impact that these technologies has. So that's it for me, and hope if you have any questions. I also like to acknowledge the work that Fraunhofer is doing, because they are the partners responsible here in MULTHEM for performing the LCA. So thank you for the data you have provided. And if you have any questions, please let me know.
Thank you both very much for your excellent presentations. And I think before we go into questions, we would like to have your feedbacks on today's training sessions. The link and the QR code for the feedback form are shared in the chat box. Please click on the link and give us your valuable feedback. And now we are ready for questions. Please feel free to unmute your mic and ask your questions or type them directly in the chat box. Thank you very much.
Good morning.
Hello.
Hello.
Yes, we can hear you.
Hello. Good morning. Thank you for these very good presentations. I have just a simple question that is simple, or just one. That if additive manufacturing will impact the end of life, or it means, do you have already some data or some conclusions or results about what is the impact on the end of life of a part that is multi-material manufactured by additive manufacturing than if it was manufactured by other process?
At the moment, we are still trying to estimate the production process, but we also, in our designs, what we are also trying to do is to have ideas how to then recycle the materials, and that includes disassembling the different components, right? So taking apart the metal from the polymer and then recycling the different streams. So that will be something that we will need to consider. At the moment, it's not in the scope of our LCA, so we will not be able to tell you the correct some quantification of this data, but it's something that we have in mind when we are redesigning multi-material products, because most of the time when you have a multi-material process, people don't go through the trouble of recycling the two different components, and the process becomes a bit more complicated, So that's why we are trying different methods how we can disassemble these products.
Yes.
In an efficient way that then the two different materials can be recycled separately.
Okay. Thank you.
If you have any questions, please feel free to unmute your mic and to ask your questions or directly typing them in the chat box. Okay, I think if we don't have any further questions, we can close today's training session. Thank you everyone for joining, and we really appreciate your support. Have a good rest of the day. Thank you, everyone.
Thank you.
Thank you. Bye-bye.
Thank you.
Bye.
Bye, everyone.